All right, so let's just start with the definition. I would like to tell you guys what a system of linear equations is. Okay, so here we go. A system of linear equations consists of two or more linear equations with two or more variables. Okay, so it's so you'll be considering like two or more equations simultaneously, and these equations will be they will contain two or more variables. So here is an example of such. So you open up this kind of curly bracket, and then you place your equations inside of this. So here's an example: 2x plus y equals 15. And 3x minus y equals 5. Okay, this is a system of linear equations in two variables. Okay, and the two variables here are x and y. Okay, and we have a special name for this type. We call this a 2x2 system of equations. We call this a 2x2, so it's like you write it as 2 times 2, but it means you read it aloud as 2x2. We call this a 2x2 system of equations. Okay, and like what are we going to do with these things? We're going to be interested in solving them. So we'll be interested in solving for which x, y values solve all of the equations in the system simultaneously. Okay. So basically, we're going to want to find like XY coordinate pairs that will satisfy all of the equations in the system. We don't want them to just satisfy one, we want them to satisfy all of them. Okay, so the way this works out is that solutions will actually come in 3 flavors, okay? So solutions, they will come in 3 flavors. And this is how it looks. Okay, so now I have a picture for you guys. Let's see. Right, here we go. Okay, so we have 3 kind of possible scenarios. So we have one scenario is an independent system in which there is just precisely one solution. Okay, so that's the first possibility. There's one solution. Second is called an inconsistent system. It's when there's actually no solution. There's no XY coordinates that will satisfy the system. And this will happen when the 2 lines are parallel and they never intersect. And the third one, the third possibility, and the third and final possibility is something called a dependent system. It actually has infinitely many solutions. The lines are coincident. I'm not familiar with that terminology, but what that means is that the lines live on top of each other in the XY plane. They're like scalar multiples of each other. Okay, so there's infinitely many points in which the 2 lines cross. Okay, and now I just have a picture that goes along with each of these three scenarios. So now let's just talk about that. So I now have a picture which highlights graphically what each of these situations look like. Okay, so the first one, independent system. Yes, you'll see there's exactly one solution. There's just one point of intersection, okay? Inconsistent is when there's no solution. You can see here the lines are parallel, all right? So, you know, these are never going to cross each other. So if you remember from our earlier work, lines are parallel precisely when they have the same slope, okay? And then the third one is the dependent system. You're going to have two lines that kind of live on top of each other in the XY plane, and there's going to be infinitely many solutions because there's going to be infinitely many points that are on both lines. Okay, so these are the three possibilities. There's no other possibilities. Each system you're given, each two by two system you're given will be one of these. All right. Good. Oh, and I just have a quick terminology note. Independent, right. So this terminology of independent, this is also called consistent. So just so if you see this somewhere else, also called consistent. Okay, so I just want to, so a synonym for an independent system is a consistent system. All right, so you may see that somewhere else. Just want to make sure you guys know that. All right, so let's just quickly let's kind of get familiar with working with these systems. So how about this example very quickly? So here's the thing. Determine if 5, 1 is a solution to the following system. So I'm going to give you a system, and we're going to need to see, is 5, 1 a solution to it? So here's the system. X plus 3y equals 8, and 2x minus 9 is equal to y. Okay, and for convenience, I will very often give a name to each of these equations. So for instance, I'm going to call this top one Roman numeral 1, a lowercase Roman numeral, and the bottom one I will denote as a lowercase Roman numeral 2. I will do that, I think, in almost every example. Okay, so how do we do this? Well, all you need to do is we need to check if x equals 5, y equals 1, solve both equations, both, not just one. They need to satisfy both equations. Okay, so you just need to substitute x equals 5 and y equals 1 into both and just verify that the equations are true. So I will check 1 first. So here's my check for 1. So I'll sub in x equals 5. So I have 5 plus 3 times 1 is equal to 8. Well, the left side is 8 and the right side is 8. So this is true. It satisfies equation number 1. Now we check 2. So if I substitute in x equals 5 and y equals 1, I'll get 2 times 5 minus 9 is equal to 1. The left side is 10 minus 9, and the left side is indeed 1. And 1 equals 1. They satisfy both, so yes. It is a solution. All right, so any questions on this? I think really the most important point here is that you need to check both equations, okay? Not just one. Okay, good. Now we're gonna dive into, given a system, how can we find the solutions, okay? What are some methods at our disposal? So the next heading will be just that, methods. Methods of solving Methods of solving a system of equations. Okay, the first one we will consider is solving by graphing. So, first one. Solving by graphing. Okay, so what is this? What's like the general model here? So one method is to graph both lines in the system. Both lines in the system. And see where they intersect. Okay, so you'll notice, like, for example, this system up here, equation 1 and equation 2, they're both lines. You can put them into y equals mx plus b form. We know how to graph those, and then you can see where they intersect in the xy plane. So that's really the strategy. So we're going to do an example now. So, example. Solve this guy, solve this system. 2x plus y equals minus 8, x minus y equals negative 1 by graphing. Okay. Okay, so we need to just graph both of these equations, and I think the best way to do it is to first put we first need to put each equation into y equals mx plus b form. Okay, and you guys will recall y equals mx plus b form has that alternate name of slope-intercept form. Okay, that was that other terminology we used. So this is not that bad. So again, I'm going to call this top guy 1. It just makes life easier. I'm going to call the bottom guy 2. I'm going to do that, I think, on every single example. So, okay, so let me deal with 1. So if you just put this into y equals mx plus b form, is really just subtracting 2x from both sides. It's y equals negative 2x minus 8. That's the first one. And how about equation 2, meaning equation Roman numeral 2 up here? Well, that's really not bad. That's just y equals x plus 1. Okay, so they are both in y equals mx plus b form, and now graphing is a simple task. Okay, so I'm actually not going to graph these guys in front of you. I actually have a nice picture, luckily. So let's just go to that. And here we have it. Okay, so we have equation 1 is the blue line here. Equation 2 is the orange. So you would graph these in the xy plane, and you just need to see, okay, what coordinate, what xy coordinate do they intersect at? And you can see immediately from this graph, it's at negative 3, negative 2. Okay, so that is really all there is to it. So now, so we see, like, visually that x equals minus 3, y equals minus 2 is a solution. Okay, now for these, for the graphing ones, I would just suggest to just go in and verify that it is a solution. So let's just verify it very quickly. For the other methods, you don't really need to verify unless you want to, but let's just go and do that quickly. So I'm going to sub in x equals negative 3 and y equals negative 2 into the first one. So I get 2 times negative 3 plus negative 2 is equal to negative 8. Now the left side is negative 6 minus 2 equals negative 8. The left side indeed is negative 8. So this is true. Now we just need to do the same thing for equation number 2. So we sub in x equals negative 3 and y equals minus 2. So what does that give us? We'll get negative 3 minus negative 2 is equal to negative 1. This is negative 3 plus 2 is equal to negative 1. And the left side is negative 1, which is indeed equal to negative 1. So it checks out. So good. So that is a solution. So we're good. So yes, negative 3, negative 2 is a solution. Okay. So any questions here? This is the only example I'm going to do with graphing. I don't think of it as a very practical method. It's kind of time consuming, and I just don't find it that interesting, to be honest. But nonetheless, it is important. All right, so like you'll have one example of graph solving by graphing on the homework, all right? Like a later homework. So any questions about anything? All right, good. So let's move on. Oh. Let's move on to a different method. Okay, so let's talk about the method of substitution. So this will be solving by substitution. Okay, so this is a little more fun, I think, than the previous method of graphing. So I'm actually going to demonstrate the strategy with an example. It's one of those where if I just write out the list of steps abstractly, it's kind of, I don't know, it's kind of hard to follow. So I'll demonstrate the strategy in real time with an example. So strategy given the system. So I'm just going to start off with a concrete example. So given the system, how about this guy? Negative x plus y equals negative 5. And 2x minus 5y equals 1. So again, I'm going to call this top equation Roman numeral 1 and the bottom one Roman numeral 2, just for convenience. Okay, so given this system, here's something we can do. We can solve equation 1 for the y variable. Okay, so let's do that. I'm going to take this equation 1 right here, this top guy, and I'm just going to solve it for y. So what will that give us? That'll give me y is equal to negative 5 plus x. Very good. Next, we can substitute in negative 5 plus x in for y in equation 2. So what does that mean? It means wherever I see a y in equation 2, so right here, I will substitute in negative 5 plus x. So let's do that. So 2x minus 5. Now it's minus 5y, but I'm substituting in negative 5 plus x for y. So I ought to open up a parenthesis. This would be negative 5 plus x. And that's now equal to minus 5. So hope everyone sees what's going on here. Okay. Now, this is an equation in one variable, and we can solve for x.
Real quick, Professor Roberts, why would it be equal to negative 5?
Why is it equal to negative 5? So I took this equation 1, the top guy, and I put it into y equals form.
Mm-hmm.
So that's negative 5, so I need to add x to both sides.
Got it. But Doesn't the second equation equal 1? You see what I'm saying?
Oh, yes, it does. Yes, sorry. I didn't know what you were referring to. Yes, it does. I appreciate that.
Yep.
Yes. Good, good. So this is now a correct equation in one variable, and we can solve this quite easily. So let's just kind of work it out. So 2x, now distribute the minus 5 into the parentheses. You'll get 2x plus 25 minus 5x is equal to 1. Okay, combine like terms and subtract 25 from both sides. You will get negative 3x is equal to negative 24. Divide both sides by negative 3, you will get that x is equal to positive 8. Good. So we have found our x-coordinate solution. Now what can we do? So the last step is now sub in x equals 8 into either equation, into either 1 or 2, and solve for y. That's the last step. So which one did I choose? Okay, I used 1, but that was completely arbitrary. I could have substituted into equation 2 if I wanted, but I used 1. So I'll use equation 1. So I go up to this guy. Wherever I see an x, I plug in 8. So it'll be negative 8 plus y is equal to negative 5. Negative 8 plus y is equal to minus 5. Good, solve this for y. Well, that's just, have to add 8 to both sides. So negative 5 plus 8 is 3. And there you have it. Those are our solutions. X equals 8, y equals 3. That's our solution. Excuse me, singular. There's one solution, not solutions. So the solution is, so you can write your solutions like how I did, x equals 8, y equals 3, or you can also write it in a coordinate pair like this, 8, comma 3. Either is fine. I think I prefer the coordinate pair, but if you just list it out as x equals and y equals, that works too. So that's really it. So I don't think it's that bad. So we'll do another example. All right, so any questions before I move on to another example of substitution? All right, so let's just get to it. Maybe I'll work a little faster on this one. Solve. So here's the system I'm giving you. X minus y equals 3, and 4 equals 3x minus 2y by substitution. So again, I'll do this in every example. I'm going to just label the top one lowercase Roman numeral 1, the bottom one lowercase Roman numeral 2. Just makes it much easier to reference them as I'm writing. Okay, so so previously we solved 1 for y. That was the previous example. We took equation 1 and we put it into y equals form. But again, that was also arbitrary. I could have solved that for x. So let me just highlight that. But we also can solve for x. All right, so let me say this again. The previous example, we put equation 1 into y equals form. I didn't need to do that. I could have put it into x equals form and then continued the strategy from there. So let me show that. I'll solve 1 for x. So that will be x is equal to 3 plus y. Okay. Now sub in 3 plus y for the x variable in the other equation, in equation 2. So equation 2 is 4 is equal to 3x, but I'm replacing x with 3 plus y. So it'll be 3 times 3 plus y minus 2y. Okay, so I hope everyone sees what's going on. I replace this x right here with 3 plus y. And that's why that's there. And now this is a linear equation in one variable, y. We can solve for y immediately right now. All right, so what does this look like? So 4 is equal to, distribute the 3 into this set of parentheses, you get 4 is equal to 9 plus 3y minus 2y. Good. Combine like terms, and you'll just get that y is equal to negative 5. Good. So that's the first piece. Now to finish, you sub in y equals negative 5 into either equation, and solve for x. Okay, so which one do I use? Oh, okay, I use 1 again. So it's x minus y is 3. So x minus, but I'm now substituting in negative 5 for y. So it's x minus negative 5 equals 3. Okay. So that is going right there. So I have a double negative. So this is x plus 5 is 3. And this is x equals negative 2. X equals minus 2. And there you have it. So the solution is, so I prefer to write my solution in that coordinate pair notation. So it's negative 2 comma negative 5. So that's very nice. All right, so any questions? Okay, so I did take the set of steps from the textbook, so I am just gonna put them here just for like the sake of completeness. But I prefer to teach the strategy using a concrete example. But I do have the general set of steps right here. So let me just put that on here. Yeah, so here are the set of steps. Maybe I'll just read them very quickly. Solve using the substitution method. So you solve one of the two equations for one of the variables in terms of the other. That's like when you put it in x equals or y equals form. You could do this for any equation, 1 or 2, the top or bottom one. Then you substitute the expression for this variable into the second equation, and you solve for the remaining variable. That's when we substitute it in, like 3 plus y for x, and then we solve for y. Substitute that solution into either of the original equations to find the value of the first variable. And then if possible, write the solution as an ordered pair, okay? And then step 4, which I did not do, was you just check the solution in both equations. You basically just have to go in and verify that your solution's correct. So it is a good idea to do that to check your work. So I would recommend checking, because if it's not true, then you know you made a mistake somewhere, so you can go back and try it again. So that's the substitution method. I will stop there with examples for this method. You'll have practice on the homework. And yeah, so any questions on this? All right, the final method of the evening. This is my favorite method because it actually has hints of linear algebra in it, which is an upper level math class. So if you take linear algebra later in your math career, you'll see remnants of this method in that class. So this is a good little warm-up to the linear algebra course. Okay, so let's now go into this. So this is now called solving a system by elimination. Okay, but I need to just put in parentheses, it's also called addition. I don't like that terminology. The textbook calls it the method of addition, but that's kind of obscure terminology. I don't really see that anywhere else. So also called addition, method of addition, but I'm going to call it elimination. That's more like the linear algebraic way to refer to it as, and I think it's more commonplace. All right, so this is very cool. So here's the idea. Here's like the rough idea, and then we're gonna jump into examples. So here's just kind of the rough idea. So the idea is to multiply one of the two equations. It's actually one or both of the two equations by a non-zero number. A non-zero number, and then add / subtract both equations to eliminate, so this is where the terminology elimination comes into play, to eliminate either the x or y variable. Okay. And that's an attractive thing, because if you can eliminate one of the two variables, then you just have one equation in one variable, and we know how to solve that. Okay, so we're just going to demonstrate the strategy with an example. So here we go. So example, solve x minus 2y equals 11, and 3x plus 5y equals minus 11. And again, I'm going to call the top one equation 1 and the bottom one equation 2. So actually, denoting this as 1 and 2 is going to be especially useful in this method. Okay, so the deal is, I want to be able to subtract these two equations from one another and get rid of one of the variables. So what if there was a 3x in front of x? And then if I subtracted the equations, I would have 3x minus 3x. The x variable would vanish. Okay, so that's kind of what I want to do. I want to introduce, I want a coefficient of 3 in front of x. Well, I can't just write 3x because that will change the whole equation, but I can multiply the whole equation 1 by 3, and that's what you do. So I will multiply equation 1 by 3. Both sides of the equation, remember, not just one side. So if I do that, you get this. You get 3x minus 6y equals 11. So now our system reads, our system is, now we have the following system. So equation 1 is now this guy. Okay. Oh no, it should be 33. Right? Yes, should be 33. Okay, excuse me. 3x minus 6y equals 33. Yeah. Okay. Let me just change this in my notes really quickly. Okay, so this is our new system with the correct right side. It is 3x minus 6y is equal to 33. And the bottom equation, equation 2, is unchanged. 3x plus 5y equals minus 11. Okay, so why did I multiply equation 1 by 3? Well, it's so if I subtract these two equations, the x variable vanishes, and I can just have one equation in one variable. So this is what you do now. So I'm going to call this 1, I'm going to call this 2. Now, if we do 1 minus 2, the x variable goes away. So I will do 1 minus 2 right now. 1 minus 2. This gives, so 3x minus 3x is 0x. Good. That was the whole point, was that we would have 0x. Now I have negative 6y minus 5y. Okay, so negative 6y minus 5y is negative 11y. And then 33 minus negative 11 is 33 plus 11, which is 44. So we have negative 11y is equal to 44. All right, so is everyone okay with what I did? I did equation 1 minus equation 2. The x variable is gone because 3x minus 3x is 0. And this is very good because I can solve this for y immediately. So this is y is equal to negative 4.
Could you have also multiplied it by negative 3?
Yes. If I multiplied the top equation by negative 3, I would need to have added the equations together. But yes, that could have worked. I like to subtract. That's the way I do it. But yeah, so Saeed, let me just repeat what Saeed said. I could have alternatively multiplied equation 1 by negative 3 and then added the two equations instead of subtracting them. That would yield the same exact thing. Okay. Good. So we have y equals negative 4. So I can now substitute in and solve for x. So now, like before, sub in y equals negative 4 into either equation. And solve for x. Okay, so which one did I choose here? I subbed it into equation 1. Okay, but that was arbitrary. Could have subbed it into any of these guys. So I'll have x minus 2y is 11. So that's x minus 2 times negative 4 is equal to 11. Okay, so that y equals negative 4 went right here. Good, and this is easy. This is x plus 8 is equal to 11, which is x equals 3. Very good. So here's the solution. So I like to put it in the coordinate pair notation. It's 3 comma negative 4. And that's it. That's the answer. So any questions on what's going on here? It's a little more involved. You need to, think for a second. You need to, the creativity comes into play when you pick which number to multiply the equation by. I picked 3 because when I subtract the 2, the x variable would vanish. So you need to think for a little bit. Okay, we're going to do one more example, and then we will be finished for the night. So last thing. Example. Oh, okay, yeah. So this example is a little different because we're going to need to multiply both equations by a different number. So let me just write that. So sometimes we need to multiply both equations. Multiply both equations by two different numbers, not the same numbers, by two different numbers before we can eliminate one of the variables. before we can eliminate one of the variables. Okay, and here is such an example. Okay, here is such an example. So here we go. Solve this guy, right? So solve 2x plus 3y equals minus 16. 5x minus 10y equals 30. Again, I will call the top one 1, the bottom one 2 by elimination. Okay, so I would like to make the coefficient of x or y to be the same so that when I subtract the two equations, one of the two variables gets eliminated. So I will do it for x. You could do it for y, but I'll do it for x. So I want to make the coefficients in front of x in both equations the same. So here's the question you need to ask yourself. How can we make 2x and 5x have the same coefficient? Okay, and we want them to have the same coefficient because I want it so when we subtract them, that it gets canceled out completely. So let's think about this. So I'm going to just set it up, but I'm not going to give you the answer. So you multiply 1 by blank and multiply 2 by blank. And let's see if you guys can come up with it. Multiply 2 by blank. So let's just give it a few minutes or like a few moments just to let everyone have a chance to think about this. But we want 2x and 5x to have the same coefficient so that when I subtract them, x goes away. Okay, and these are going to be two different numbers here. All right, so let's just give it a minute.
Just multiply 5 by 2 and 2 by 5. Get them to have 10x.
Right, so you want to multiply equation 1 by what?
By 5.
By 5. Okay, that's good. And you want to multiply equation 2 by what?
By a 2. Good.
That's the right thing to do, because if I multiply equation 1 by 5, that will create a 10x. And if I multiply equation 2 by 2, that will also create a 10x. And that's what we need.
Quick question. If you always multiply by the coefficient of the other one, it will always like end up right?
Yes. Yes. You can always multiply by the other guy. Yes, that will always work for sure. So if I do this, if I carry out these operations, multiply 1 by 5, 2 by 2, you get, what do we get here? Well, we get this system. So multiply the top guy by 5, right? So you get 10x plus 15y is equal to, well, negative 16 times 5, I have that worked out already. I can't do that in my head. That's negative 80, okay? Multiply equation 2 by 2, that's a little more doable in your head. That'll be 10x minus 20y is equal to 60. 10x minus 20y is equal to 60. So again, I'm going to call the top one equation 1, bottom one equation 2. Just makes things easier. And now we are in a very nice position because I can subtract 1 minus 2, and I will just have an equation involving the y variable. So this is a very attractive situation. So equation 1 minus equation 2 gives, well, 10x minus 10x is 0x. Well, we rigged it so that would happen. Now I need to do 15y minus negative 20y, which is the same as 15 plus 20, 15y plus 20y. That's 35y. Now I'll do negative 80 minus 60. That's negative 140. Good. And now this is a linear equation in the variable y, which we can solve for quite immediately. So divide both sides by 35, and this works out nicely to be y is equal to minus 4. Okay, you're not done yet. You do need to now sub in y equals negative 4 into either of the equations. So I picked equation 1 again. So sub in, so let me just write that, sub in y equals minus 4 into equation 1 to find x. Okay, so 2x plus 3y. So the 2x plus 3 times negative 4 equals negative 16. So that's coming in right here. That's y. And I've solved this for x, so this is not really bad. This is 2x minus 12 is negative 16. Add 12 to both sides, you'll get 2x is equal to negative 4. Yeah, negative 16 plus 12 is negative 4. And this is x is equal to negative 2. Very good. So the work is done now. I just like to compile our final answer into this xy coordinate pair notation. So the solution is negative 2 comma negative 4. Yes.